I'm so happy and excited to welcome you back to Organic Chemistry Season 1, Lesson 2. In this lesson, we are going to be looking into hybridization. What do we mean by hybridization? When we say hybridization, we are looking at the merging of two or more atomic orbitals of different energy levels to form new orbitals with the same energy level and the same number of orbitals, which are better for covalent bonding. There are things I want you to take note of here. First note: sigma bonds are formed by hybridized orbitals, and there cannot be more than a sigma bond between two atoms. Second note: pi bonds are formed by unhybridized orbitals, and between two atoms, we may have 0 pi bond, 1 pi bond or more. Third note: a pi bond can only occur where a sigma bond has been bonded. But it is possible that we may not even have these unhybridized orbitals in carbon atoms. There are three major types of hybridization in carbon atoms. We have sp hybridization, sp2 hybridization, and sp3 hybridization. When we say sp hybridization, we are looking at s orbital bonding with one of the p orbitals. For instance, if we have this s orbital bonding with this particular p orbital, which we can say it is px. So we have 2s and 2px coming together. They form sp orbitals. Mind you, there are two orbitals here. They have the same energy. But before now, p orbital is greater than s orbital. It is no longer s orbital nor p orbital, rather sp orbitals. Let's assume that we have two carbon atoms having these sp orbitals. Here, we have carbon A and carbon B with two sp orbitals each from the two carbon atoms. Let's assume that the electrons from hybridized orbitals are being denoted with the color red, and the unhybridized with this green. Look at how I arranged it here. Okay? Remember we said that between two atoms like carbon A and carbon B atoms, we cannot have more than one sigma bond. And that sigma bond comes from two orbitals of two atoms. Look at this. This one unpaired electron from the hybridized orbital will bond with one unpaired electron of the hybridized orbital of carbon B. So first of all, there's combination between carbon and carbon. So the remaining red electrons here are better to be bonded with any other atom, and can no longer bond with this carbon. Now, the green unpaired electrons are still ordinary p orbital. It has not changed its name, but these red ones have changed their name to sp orbitals, but these p orbitals are still answering p orbitals. Pi bonds are formed around the sigma bond, since a pi bond can only occur where a sigma bond has been bonded. Here we are having two pi bonds from four unhybridized orbitals. We can also do the same thing in sp2 hybridization, where we have one s orbital bonding with two different p orbitals. For instance, we can say px and py, as you can see on the screen. What happened here is that we can assume that we have formed sp2 hybrid orbitals. Look at this, we have three orbitals in this, and each of the orbitals have an unpaired electron. So if we have two carbon atoms coming together with this sp2 hybridization, how do they bond? Remember, we can only have one sigma bond between two atoms. The two carbon atoms catenate the two sp hybridized orbitals containing one unpaired electron each, contributed by each of the carbon atoms in covalent bond. The four unpaired electrons from the two hybridized orbitals remaining bonds with other atoms. But we have only two unhybridized orbital. This unhybridized orbital now can bond with the carbon because they can only bond on the point where we have already gotten a sigma bond. It forms a pi bond resulting to double bond. But while this orbital is dragging to bond here, the shape of this molecule changes, as you can see. If you're looking at sp3, we have an s orbital bonding with the three p orbitals. We have 2px, 2py, 2pz, all are used for bonding. No unhybridized orbitals. So I am using all red for this. Remember that we cannot have more than one sigma bond between two atoms. So the remaining 6 sp3 orbitals can be used to bond with any other atom including carbon atoms. Therefore, sp hybrid forms a triple bond and the bond angle is 180 degrees. Linear shape, with 2 pi bonds. Primarily seen in alkynes. With general molecular formula as CnH2n-2. sp2 hybrid forms a double bond and the bond angle is 120 degrees. Trigonal planar shape, with 1 pi bond. Primarily seen in alkenes. With general molecular formula as CnH2n. sp3 hybrid forms a sigma bond and the bond angle is 109.5 degrees. Tetrahedral shape, with no pi bond. Primarily seen in alkanes. With general molecular formula as CnH2n+2. In naming compound with a triple bond between two carbon atoms, ended with YNE. Inserting a number where the triple bond occurred. In naming compound with a double bond between two carbon atoms, ended with ENE. Inserting a number where the double bond occurred. Both triple and double bonds are said to be multiple bonds. They are generally called unsaturated carbon-to-carbon bonds. In naming non-multiple bonded compounds, you ended with ane. By chemical reactions. Combustion reaction is general for organic compounds. The triple bond has the ability for addition reaction, addition polymerization reaction, oxidation reaction, and substitution reaction. If the triple bond between the carbon-to-carbon is seen as number 1, the type of substitution reaction will include acetylide ion formation. The double bond has the ability for addition reaction, addition polymerization reaction, oxidation reaction, and no form of substitution reaction. Now, they are all sigma bond, because they have already strong bonds and are saturated carbon-to-carbon bonds, they are less reactive. They only undergo combustion reactions and nucleophilic free radical substitution reactions, aided by ultraviolet rays. From their reactions, we can distinguish them in the laboratory. To distinguish between saturated and unsaturated carbon-to-carbon bonds, use the addition reaction of orange bromine water at room temperature. The multiple bonds, or the unsaturated carbon-to-carbon bonds, turns it colorless. But the saturated carbon-to-carbon bond has no effect on bromine water. Or we can use the oxidation reactions. In these reactions, there is addition of purple acidified potassium permanganate or orange acidified potassium dichromate to multiple bonds, which will change to colorless and green respectively. But the all-single bond, that is the saturated carbon-to-carbon bond, has no effect on them. Only the terminal triple carbon-to-carbon bonds changes the color of ammoniacal silver nitrate or ammoniacal copper 1 chloride, from colorless to silver mirror and red respectively. So we can distinguish the multiple bonds with this reaction. The single bond has no effect on it. Thank you very much for watching this video to this extent. In our next lesson, we will be looking into the uniqueness of carbon atoms. Be there.